So in this section, section 6.7, we're going to talk about the hyperbolic trigonometric functions. And these are the hyperbolic sine, hyperbolic cosine, hyperbolic tangent. And I guess I may as well also include in this list hyperbolic secant. Okay. And so we say this H here is for the hyperbolic. So this is sinh, cosh, tanh. And so that's kind of the shorthand for these hyperbolic sine, hyperbolic cosine, hyperbolic tangent. And if we were to graph these functions, sine of sinh of x, hyperbolic sine, basically when x is large, this e to the negative x is going to be tiny. And this is going to look like e to the x over 2, or basically just an exponential. Okay, so it's going to look something like this, and it's going to grow exponentially. So anyways, it'll look like that. When x is negative, the dominant term is going to be e to the negative x. So when x is negative, e to the x is going to be really small. And this is going to look like, this is going to look like negative e to the negative x over 2. So it's going to look something like that. And then these grow super, super rapidly. Okay, and so they shoot off to infinity. And as x moves further and further to the right, these values get higher very quickly, exponentially quickly. Okay, so that's what sinh looks like. Cosh is going to look like, so hyperbolic, so that was hyperbolic sine. Hyperbolic cosine is basically going to look like a U, not quite a U. It's not a parabola. It looks kind of U-shaped. In fact, the St. Louis arch was modeled on an upside down hyperbolic cosine curve. So if you were to actually go to the, you can look up what the actual curve is that was used to model the St. Louis arch. So the St. Louis arch is an upside down hyperbolic cosine. And then there's also hyperbolic tangent and hyperbolic cosine, which I'm not going to draw. Okay, and so we can do all sorts of things and talk about derivatives of these functions and so on. Hyperbolic tangent, by the way, is a function that is one-to-one. It's going to have an inverse. And so I just want to talk about a few things with that. So same with hyperbolic sine, right? It's one-to-one. We can find an inverse and so on. Okay. So before we talk about derivatives of inverses, let's talk about the derivative of the original function. Sinh of x is defined as e to the x minus e to the negative x over 2. And so if we differentiate this, what's going to happen is the derivative of, the 1/2, we can basically just tag along. The derivative of e to the x is itself. The derivative of negative e to the negative x is going to be plus e to the negative x. And so the derivative of hyperbolic sine is hyperbolic cosine. Likewise, the derivative of hyperbolic cosine, so this is hyperbolic cosine is e to the x plus e to the negative x over 2. When we differentiate, we're going to get e to the x minus e to the negative x over 2 from the chain rule of, the 1/2 tags along, derivative of e to the x is itself. The derivative of e to the negative x is minus e to the negative x. And this is hyperbolic sine. So it turns out that sinh and cosh are derivatives of each other. And we also get things like if you differentiate hyperbolic tangent, you end up with hyperbolic secant squared. Okay, and I'll let you fill out the details there, but that turns out to also be the case. And then you get similar identities for the other hyperbolic trig functions. And these are useful, and these are things that come up all the time. Hyperbolic cosine comes up, like I said, when we're talking about the St. Louis arch. Hyperbolic cosine, I circled the derivative of hyperbolic cosine, but hyperbolic cosine comes up all the time. If you were to ever see, if you're driving down a highway or driving down a road and you see two light posts or two utility poles, and then you kind of see the wire between them hanging down, the wire actually hangs in the shape of a hyperbolic cosine curve. It's not a parabola, it's a hyperbolic cosine curve. So these are things that come up naturally in natural phenomenon, all the time. And so that makes them useful to study and to know. Yeah, so that's really the highlights of what I wanted to say in 6.7, except that hyperbolic tangent is a one-to-one, one-to-one function. It has an inverse. And that means that you can talk about its the derivative of the inverse of hyperbolic tangent. And it turns out when you do this, what you're going to get is 1 over x squared minus 1. And so in and of itself, hyperbolic tangent and inverse hyperbolic tangent might not come up a lot, but there's going to be a lot of problems where knowing the integral of 1 over x squared minus 1 is going to be useful. There's going to be another method that we'll talk about of integrating called partial fraction decomposition, where we'll integrate things like 1 over x squared minus 1. But it turns out that that just has an antiderivative, and the antiderivative is a little complicated, but it's the inverse hyperbolic tangent of x. Okay, so again, another useful thing for us to know. So I've put it on our handout of all the stuff to know. I'm going to leave it to you to go through all of the 6.7 exercises. We'll do some stuff like this in class next week, or the week that, again, it depends on when you're watching the video. But yeah, so I'm not going to go through any more exercises. I would encourage you to look through the book and all the exercises that are included in the book and try as many practice problems as you can beyond the homework. And like I said, I'll have some problems on the worksheet when we get to that in class. Okay, but that's enough on 6.7.